this video, we're going to carry on talking about the microscopic oscillator model, and we're going to actually apply the formula that we derived in the last video to a variety of different dielectric systems, such as gases, solids, basically tinkering around with the equations that we've been deriving and seeing what predictions we can get as a result. And we're going to be deriving what's known as the dispersion relation, which basically relates the frequency of the radiation to its dielectric properties, such as refractive index, permittivity, that kind of stuff. So let's jump right into it. So in previous videos, we have discussed the formula that the polarization, the macroscopic polarization, is equal to epsilon naught multiplied by chi, which is the electric susceptibility, times the electric field. So there's kind of like a linear relationship between the electric field, the external electric field this is, and the macroscopic polarization that the dielectric experiences. And we've also shown that if the system is sufficiently dilute, which means that all of the dipoles that cause the polarization are sufficiently far apart, then we get that the polarization is equal to the number of dipoles per unit volume multiplied by the polarizability multiplied by the electric field. But this is only if the system is dilute. And this is what happened when we had the Clausius-Mozotti relationship in the dilute limit. But we also said that this could also be expressed as epsilon naught, and instead of the electric susceptibility, we can write it in terms of the electric permittivity, the relative permittivity. Remember, this is a dimensionless quantity and is simply the relationship to the actual permittivity and the permittivity of free space minus 1 times the electric field. So we have P and E right here, and then we have a bunch of constants that relate the two together. So what we can now say is we can say that this set of constants is equal to this set of constants right here. So we can say that epsilon naught is times epsilon r minus 1 is equal to the number of dipoles per unit volume times alpha. And remember, this is all in the dilute limit. So rearranging this a little bit, we're going to get that the relative permittivity is equal to 1 plus n alpha divided by epsilon naught. But of course, we said in the last video that the polarizability is a function of the driving frequency of our system is this formula right here. So what we can essentially do is we can substitute in for alpha this big formula right here. So we're going to get 1 plus n divided by epsilon naught e squared divided by m. We're just going to add our oscillatory term, which has got all the various different frequencies. So just to distinguish, what I'm going to do is I'm now going to drop the D and I'm just going to write it as omega. So omega naught is of course our resonant frequency of our kind of spring-like thing. And omega now is just the driving frequency right here. So I'm dropping the subscript D just because it looks a little bit like an O, so it's quite easy to get confused. Now in a typical system, what we actually find is that there are various different resonant frequencies. So this omega naught, and in fact this gamma as well, isn't going to be the same across all of the atoms within the dielectric, because most dielectric materials are going to be comprised of more than one type of atom or molecule right there. So typically this will result in different frequencies. These omega zeros will be different. But for now, we're just going to assume that there is only one omega naught. That's just for simplicity. But more generally, you're going to find that there are more than one resonant frequencies. So with that assumption, we're going to attempt to derive, as I said, the dispersion relationship, which is that of frequency, this driving frequency right here, omega, and the dielectric properties such as refractive index and stuff. And we're going to apply this for a bunch of different cases. And we've started out with the dilute limit. So let's change gears a sec, and we're now going to think about how waves, just any electromagnetic waves, propagate in air. The speed of any wave is equal to, or any electromagnetic wave that is equal to c in a vacuum. But of course, we're not in a vacuum, we're in a dielectric of some kind. We're in some medium where the electromagnetic waves are going to be slowed down or kind of stopped entirely if it's like a metal or something. And so for a general medium, we introduce the quantity known as the refractive index. And that basically says this is how much the electromagnetic wave's speed is reduced by within this medium. And n is always greater than 1. But what do we say about waves in general? So what is the most simple wave equation, essentially? Well, we know that the wave speed is equal to the frequency times its wavelength. So now what we can say is that the frequency times the wavelength is equal to the speed, which in this case is c, divided by the refractive index. So this would be true of any electromagnetic wave. But instead of talking about linear frequency, we've been talking about angular frequency. And we define angular frequency as being 2 pi times the linear frequency, f, right here. And we can actually do a very similar thing with the wavelength, lambda. So instead of talking about wavelength, what we actually talk about quite a lot in certainly condensed matter physics and electromagnetism is the wave number k. And this is defined as 2 pi divided by lambda. And in fact, more generally, this quantity k is actually a vector. And so rather than calling it a wave number, just like this, if we're talking about a wave that's propagating in more than one dimension, or if we're just, applying more dimensions to our system, which we like to do, at this level, then we actually define k as being equal to kx in the x direction plus ky in the y direction plus kz in the z direction, right there. So this could be a wave that's propagating in any single direction right there. But of course, lambda is just going to be the same because it's a scalar quantity. Lambda is just going to be the same. However, the actual k wave vector is going to be telling us about what the direction the wave is propagating in as well. So this could be for any kind of wave, but for now what we're going to do is we're just going to assume that the wave is propagating in the x direction. So that means that ky and kz are equal to 0. And this we often do just for simplicity because it makes the maths a lot easier to consider a wave just propagating along one of the axes. So we're going to say that k is equal to kx in the x hat direction. And of course we said that kx is equal to 2 pi divided by lambda right there. So let's go ahead and substitute in, rather than for f and lambda, we're going to substitute in for omega and k. So instead of f, we're going to get omega over 2 pi. And instead of lambda, we're going to get 2 pi divided by k, which is equal to c divided by n. 2 pi is going to cancel, so we're going to get omega over k is equal to c over n right there. Of course, I should be writing that this is the x component of k. And so rearranging for the x component of k, we're going to get that kx is equal to n omega divided by c right there. Now what we can define is we can define k naught as being the wave vector, and we actually should probably put an x right there, in free space. So this essentially means that this is what our k value will be if the refractive index is 1. So this is in a vacuum or something. So if our refractive index is 1, then that's just going to be equal to omega divided by c right here. And so what we can now say is that kx, which is our x component of the wave vector within any material, is equal to k naught in the x direction multiplied by the refractive index right here. Now, it was actually James Clerk Maxwell that made the discovery that electromagnetic waves will always travel at the speed of light in a vacuum. And the way in which he derived this was by using Maxwell's equations in order to figure out that the speed of light, c, is related to the permittivity and the permeability of free space. And it was related by this equation right here. It was 1 divided by the square root of mu naught times epsilon naught. And mu naught and epsilon naught are the permeability and permittivity of free space, respectively. But this is in free space. We can actually generalize this to being in any medium. So let's go ahead and talk about our velocity v again of our wave. This would be equal, so if this is the case in free space, then we're going to get a very similar looking equation, except rather than with mu naught and epsilon naught, we're just going to get what the permeability is in any material multiplied by what the permittivity is in any material. So these are not the dimensionless variants of the quantities. So just to remind, epsilon without any subscript is equal to epsilon naught times epsilon r, where epsilon r is the relative permittivity. And same goes for the mu, the permeability, which is equal to mu naught, which is the permeability of free space, times mu r, which is the relative permeability. So let's go ahead and, instead of writing this in terms of just mu and epsilon, we're going to write this in terms of mu naught and our relative permittivities and permeabilities. So we're just going to simply get a chunky square root, which is mu naught mu r times epsilon naught epsilon r, right here. And then we can separate this into 1 divided by mu naught epsilon naught, because of course we can just simply factor out square roots quite easily, multiplied by 1 over mu r epsilon r. But of course we said that 1 divided by mu naught epsilon naught is simply equal to the speed of light, c, right here. This is what Maxwell derived. So we get that v is equal to c times 1 over the square root of mu r epsilon r. But of course we said that v is equal to c divided by n. So therefore, if we divide both sides by the speed of light and then just kind of flip it over, we simply get that the refractive index is equal to the square root of mu r times epsilon r, right here. Now, in a lot of cases, and this is going to be the majority of cases we're going to be considering within this module, the relative permeability, mu r, is very, very nearly always going to be 1 right here. Now, this basically means that within a lot of materials, you're not going to get a great deal of magnetic response. And there's actually a good reason for this. And the reason is that the magnetic field is so much weaker in magnitude than the electric field, when you're talking about electromagnetic waves, that is. So basically, this is then going to simplify nicely down to the refractive index being equal to simply the square root of epsilon r. And now we can plug in our value for the permittivity that we derived earlier into this in order to obtain an expression for the refractive index of our system, which is being driven by an electric field. So this is going to give us a refractive index, which is going to change as a function of the driving frequency. So what are we going to get when we substitute this in? Well, we said that the relative permittivity is equal to 1 plus ne squared divided by epsilon naught m, all times 1 divided by omega naught squared minus I gamma omega minus omega squared. And this is all going to be under the square root, so we have to raise this to the power of 1/2. Now, we said that we were talking about a system which was sufficiently dilute. Now, what does this mean in terms of the algebra? Well, this means that n right here is going to, in fact, make this entire expression relatively small because, of course, e squared, epsilon naught, and m, they're all just constants right here. And in this factor right here, that will have a variable component. However, this n is going to be one of the biggest factors in determining whether this whole term right here is going to be much, much bigger than or much less than 1 right here. Because essentially that's what we're trying to ascertain. Does this term pale away into insignificance compared to 1? And if it does, then we can use a very handy approximation, which hopefully you guys are familiar with, in that 1 plus x to the power n is approximately equal to 1 plus nx if x is small. So because we said that n is sufficiently small, we can go ahead and use this, and we're going to get that n of omega is equal to 1 plus ne squared divided by 2m epsilon naught times this factor right here. So there we have it. We have this expression for the refractive index of our medium right here, our dielectric medium. And it's going to be a function of the driving frequency of our electric field that we are applying to this system right here. And now we can predict what the refractive index is as a function of the frequency. So when we plot this out, we're actually going to get two graphs essentially, because of course this is not a real expression. We have an I term right here. This in fact what makes this equation complex. So you're actually going to get a real component and a complex component to it. So let's go ahead and plot out the real part right here. We're going to get something that looks a little bit like this. So this is our frequency versus refractive index axis right here. So we're going to get refractive index on the y-axis, and we're going to get frequency along the x-axis right here. So I'm going to do the real part in red and the imaginary part in blue. So the real part is actually going to do something a little bit like this. So it's going to be fairly flat until it reaches a point, and I'm going to tell you what this point is in a sec, where it actually does something a little bit like this, which is very weird. So it actually goes up, but then actually becomes 0 and then even negative for very, very high frequencies. But of course we have a complex component as well. And this is actually going to have a more simple curve. It's actually just going to go sort of up like that and then kind of down like that. So it's just going to have sort of one kind of peak right along there. And we'll actually go into what the complex component of the refractive index means in a later portion of this video. So this is the curve that kind of emerges as a result of this, but a lot of this has a lot of physical significance right here. But this part right here, so the point where the interesting stuff happens, you could say, is the resonant frequency, omega naught, right here. So you actually find that the point where you get this kind of resonance, so this really big response in the refractive index, is omega naught right here. And another thing to note is that the width of this kind of resonance peak is actually determined by gamma right here, the damping constant. So gamma is kind of related to what the width is, and omega naught is related to what position along this kind of frequency spectrum this kind of peak, or resonance, I should say, occurs at. So that is our function for a refractive index as a function of frequency for a dilute medium. So now we're going to go on to consider the polarizability of a solid. Now, this is going to be a little bit different to what we were talking about before, in that this is not going to be dilute. So what we said with systems such as these is that this n term right here, the number of dipoles per unit volume, is sufficiently large. So if we go back to the Clausius-Mozotti relationship, we find epsilon r minus 1 over epsilon r plus 2 is equal to n alpha divided by 3 epsilon naught. We actually find that this n alpha term is much, much bigger than the 3 epsilon naught term, which wasn't the case before right here. So whereas before we had that n alpha is equal to epsilon naught epsilon r minus 1, and this was for the dilute case, we can't actually make this approximation for this case because n is not sufficiently big in order for us to justify that. So when we're rearranging this to find n alpha, we're going to just simply get the whole equation. We're going to get n alpha is equal to 3 epsilon naught times epsilon r minus 1 over epsilon r plus 2. Putting this back to epsilon r minus 1 over epsilon r plus 2 is going to be equal to n alpha divided by 3 epsilon naught. So let's go ahead and substitute alpha, which is what we derived in the previous video, which is our frequency dependence of the polarizability. And we're going to go ahead and get n over 3 epsilon naught times e squared divided by m times our factor right here. So we have a much more complicated expression for epsilon r right here, which is going to make it a little bit more difficult to produce a graph in the same way that we did before. But what we can actually do is we can consider the low frequency and the high frequency limits. And when I say frequency, I'm talking about the driving frequency, of course. So let's go ahead and consider what's going to happen when this omega term right here is low. Well, if your driving frequency is really, really low, then this omega squared is going to be pretty much negligible. So because you have a very small number that's kind of being squared, so it's going to be really, really, really small. And in fact, what we can also do is we can also not really bother with this term either, because of course, if the frequency is really low, there's not going to be a lot of damping. There's not going to be a lot of collisions between the electrons within our system. So we're actually just going to end up with Ne squared divided by 3 epsilon naught m times 1 divided by omega naught squared. So this is in kind of like the limit, and this very much is an approximation as to what's going to happen. But generally what you find if you have a low frequency electric field that's driving the system, you find that the dispersion relation is kind of just related to the resonant frequencies right here. And so you actually get kind of a curve that looks a little bit like this. This maths can get very tricky for this, but you essentially find that every time there's a resonant frequency, of course we said that there was only one resonant frequency in our system, but if you have a more realistic scenario where there's lots of resonant frequencies, you get kind of a curve that sort of does something like this. And this is in the low frequency limit right here. So yeah, not that much of an interesting result. You find that for low frequencies, you just get that the spectrum just kind of changes slightly whenever you get to these frequencies, which in our system, there's only one. That's what you find for a insulator which is compact, so it's not dilute.